Okay, so we looked at the normal distribution and we saw that the standard normal distribution, where the average was 0, variance was 1, which also means the deviation is 1, and we had a table of values which allowed us to find all the results we needed to. So now what we'd like to be able to do is to turn any normal distribution into the standard one, and then we've got the table of values that we can use to find our answers. So Z is going to be my random variable. That's going to represent the random variable for the normal distribution. So average 0, variance of 1. So the probability distribution function becomes the standard one. Now what has happened? Y equals, if I now divide this by the deviation, what would happen to our curve? And we've seen, well, that would have a stretching effect. And we'd end up with this new function. But remember, the area under the curve has to remain to be 1. Now if I stretch the curve, the area under the curve is going to change. Right? So it started off, let's imagine it's a rectangle to make life easier. We'd start off with a rectangle, base times height is equal to 1. So we know the area is 1 and we've got to keep it at 1. But we're now changing it to say, hang on, it's now the deviation times base times height. And we want that to equal 1. But actually, it's now going to equal the standard deviation, because we know b times h is 1. So how do I get that back? Well, now I need a vertical stretch, which would divide it by the deviation, because then I'd go, all right, well that one area, which we now know's got an area of standard deviation, but I'm going to multiply it by 1 on the deviation. That'll get it back to an area of 1. So we need to do a couple of stretches to get into what we want. So stretching it vertically is the same as dividing by the 1 on the standard deviation. We will end up with that lovely expression, but now I'm going to shift it. I'm going to shift it right by the average, which will get that curve centered on 0 instead of the average being wherever the average is. I want to move the average so the average is 0. Just shifting it horizontally is not going to change the area. So that's fine. I can shift it as much as I like. So I end up with this. So what we've just proven, do not panic, you do not have to prove this, I'm just showing you where it comes from, is that a random variable which belongs to a normal distribution with average of 0, variance of 1, is equivalent to a random variable which is just any normal distribution which has an average of mu and a variance of omega squared. The transformation then, capital X, will be this z minus mu over the standard deviation. So that's the key. That's what we need to know. That's how we're going to transform things to a standard normal distribution, which basically brings up z-scores. So all normal distributions can be converted to our standard one using that standardisation equation. And that's essentially how, when I give you your test back and you got your z-score on, that's exactly how I work out your z-score. I get your result, subtract the average, divide by the deviation. The result of that, as I say, is called the z-score. And as I've mentioned before, z-score is basically how many deviations you are away from the average. Okay, so what about quartiles and outliers under this standard normal distribution? Well, a quartile, we know, well, I'm talking about the third quartile here, would be when the probability is 0.75. We've got 3/4, the cumulative probability. Now, if I look at my tables, what I'm basically saying is, which one would give me an answer of 0.75? So I'm sort of reading the tables backwards. I'm looking for 0.75, and it's 0.67 gives us that result. So by symmetry then, Q1 must be negative 0.67, which tells me the interquartile range of any normal distribution is going to be 1.35. An outlier, we said an outlier is going to be greater than Q3 plus 1.5 interquartile ranges. And so if I sub those numbers in, we get 2.7. So anything further than 2.7 deviations from the mean, we would consider that to be an outlier. Okay, well, let's look at some questions then. How we use this idea. We're in the chemist waiting for our prescription to be prepared, and we know that the waiting time happens to be normally distributed. That's lucky. The average waiting time is 15 minutes, and it has a standard deviation of 2.8 minutes. What's the probability that we'll be waiting more than 20 minutes? Waiting more than 20 minutes. So I'm going to let W represent the waiting time in minutes. So waiting time is normally distributed with an average of 15 and a variance of 7.84. Well, they told me the deviation, but in our notation it's the variance we write down, not the deviation. So using our formula, probability that W is greater than 20 would be the same as the probability in a standard normal distribution that Z is greater than 20 minus 15 divided by 2.8. So to work that one out, that's going to be 1 minus the phi of 25 on 14, which I can now plug into my calculator if I'm using that, or look up our table of values, and we get 0.03707. So actually, quite a small probability we'll be waiting more than 20 minutes. So we'll keep using that particular chemist. They're good. The TQ company. TQ, I have no idea. TQ. Maybe it's just a polite company. Thank you, yeah. The TQ company makes a soft drink sold in 330 milliliter cans. The actual volume of the drink, though, won't always be 330 milliliters. We know it's distributed normally, and there's a deviation of 2.5 milliliters. Now, we want to make sure, because we want our customers to be happy, we want to make sure that at least 99% of the cans will contain more than 330 milliliters. Certainly, we don't want it to be less than that, or people are going to get upset. So the machine that's going to put the drink into the can, what should we set it at? So what volume should we set it at to put it into the can so we know we're going to get 99% was chance of there being more than 330 mils when it distributes the fluid. So V is going to represent the volume of the drink. So V is normally distributed. This time we don't actually know what the mean is, so that's what we've got to work out. And the variance for this one is 6.25. We want to know the probability of V greater than 330, or rather, they've told us that probability. We know what it is. But that would be equivalent to the probability of Z being greater than 330 minus whatever the average is over 2.5. That's the probability. Why is it 0.01? Because I'm going greater than 330, and greater than 330 would be 0.01. So we need to use our tables to find 0.01. Problem is, our answers only start at 0.5. So therefore, we'll look for 0.99 in our tables. Now, if I look up 0.99, closest I have to 0.99 is 0.9901. So that's not a bad one. So that's 2.33. Therefore, by symmetry, the one I want for 0.01 is negative 2.33. So now we just rearrange it, and there's our average, 335.8. So if we set the machine at 336 milliliters, we should be okay. We'll get the 99% probability of there being more than 330 mils in the can. Biologists do all sorts of crazy experiments. This particular biologist has been interested in the heights of cactus. And they've noticed that 34.2% of the cacti are below 12 centimetres. 18.4% of the cacti are above 16 centimetres. Now, assuming these heights are normally distributed, what's the average and the deviation? So we're going to find both this time. So H is going to be the height of my cactus. Normally distributed, but we don't know either. We don't know what the average is, we don't know what the variance is. So the probability that it's less than 12 minus mu on sigma, the probability that it's greater than 16 minus mu on sigma is 0.184. So the cumulative probability, 0.342 for the left one, but the cumulative probability on the right hand one would be 0.816. Now, once again, 0.342 is less than 0.5. So in the table, I need to look up 1 minus 0.342. And that, so I need to look up in my tables 0.658. So we want to know what gives an answer of 0.658. Looking at our tables, 0.658. Well, we've got 0.6591 and 0.6554, so it's somewhere in between 0.40 and 0.41. Well, it's closer to 0.41, so I'm going to say 0.41, but therefore I want negative 0.41. And 0.9 gives us the result of 0.816. We don't have simultaneous equations. So playing with our simultaneous equations, well, I'll eliminate the average, and we get that the deviation is 3.05. Summing back in, there's our average, 13.25. So I think the tricky bit about these one is reading the table backwards, getting the right number.